And probably more justification than you needed, but it's basically me saying, I don't just teach this concept or reintroduce it, reinforce it to be difficult. To say, well, I know you like it this way, but because I'm a teacher and teachers do this all the time, we're like, oh, we know you like to do it this way. We're going to make you do it the hard way. You know, it's not like that. This is the beneficial way. This is the way that leads to greater understanding. Right? So that being said, what? We have degrees. We got these dashes here, and then we have these almost like sleepy faces or something. So we have the degrees. That's the obvious thing. The little dash here is for the radian equivalent. All right, we've had our calculators in radian modes all year, except for one activity, for a reason. All right, because a radian is a linear measure, and when you have a trig function in radian form, it allows you to compare that trig function to other types of functions that are not trig, like polynomial functions, radical functions, things like that. All right, if it's in degree form, it's apples and oranges, because in order to graph a sine wave, if you're in degrees, you'd have to have an x scale from 0 to 360 degrees. Whereas if you're in radian form, you can still do it in 0 to 10 or negative 10 to 10, if you like that. You know, a standard zoom, rather than manipulating it so you can see the trig function, then manipulating the window again so you can see the polynomial function. Right? So it takes apples and oranges, makes it apples to apples. Right? So that's the strength and the benefit of the radian measure. The coordinates, I heard somebody asking, or somebody saying, I got everything except for the coordinates. And that's fine. We're going to learn how to do that. And in fact, that's where the hard chart is going to be the most beneficial. Because if you know that, then you already know the coordinates here. It's just a matter of taking what you know from the hard chart and transposing it here in the correct places. All right? But what are the coordinates in a unit circle? The coordinates, x comma y, correspond to the cosine and sine of particular values. So x and y is the same as cosine of theta comma the sine of theta. All right, and what that tells us, well, it tells us a bunch of things related to identities. You remember those trig identity verifications, get left equal to right, those were fun. You can do a lot with that, but even more basic than that, it's telling us that if I know the angle and I know the coordinates, then I know the cosine and the sine ratios of that angle. So if I'm at 30 degrees and I know the coordinates there, I now know that the cosine of 30 degrees is the x value and the sine of 30 degrees is the y value of that ordered pair. So, great, cosine and sine. What about the other ones? Well, we know tangent is sine over cosine. We know secant is 1 over cosine. Cosecant is 1 over sine. Cotangent is cosine over sine. So as long as you know these two ratios, you could always figure out the other four. Right? So just by knowing coordinates, we have an avenue to help us get these ratios very quickly and easily. And then the other question would be, well, why these angles? The angles that we're about to include. Why these particular angles? The easy answer to that is actually very straightforward. It's because those are the ones that give us nice numbers. Right? We choose the angles we choose because they give us clean values. It's all based on geometry, 30, 60, 90 right triangles and 45, 45, 90 right triangles. All right, so all stuff you've seen before, but maybe in a different way. All right, so we start off with the basics. 0 degrees corresponds to 0 radians and has a coordinate of 1 comma 0. All right, the way it's defined is that 0 degrees is, I mean, if you're going north, south, east, and west, 0 degrees is east for some reason. It seems like it's math people just being unnecessarily complicated. Like 0 degrees is north everywhere else, but for some reason we have to make it east. We make it east because it corresponds with the XY plane, the XY axes. All right, so everything kind of falls apart if that's not the case. And in fact, we could, if we wanted to, we could make this 0 degrees. We could make 0 degrees due north. but then x and y axes would have to get reversed. So if you were plotting, like a parabola or something like that, you would be plotting y against x instead of x against y. All right, so it would change, it would reverse every single thing. So they're like, well, instead of changing every aspect of algebra, why don't we just make 0 degrees go east? All right, so that's the answer to that question that's been plaguing you for the last 2 years. So anyway, how many degrees would there be in one full turn around a circle? 360 degrees. Do we know how many radians that corresponds to? 2 pi. All right, that's actually all the information you need in order to determine every single radian measure in this entire circle. Right? Because I'm sure you learned the at some point the conversion factor multiplied by pi over 180 sometimes, and other times multiplied by 180 over pi. Which case do I do which? I don't know. It's not even that complicated. When I teach pre-calc algebra 2, I don't even bother with that. You know this fact, because everything else is built off of it. All right, I want 180 degrees. All right, 180 degrees is half of 360. I need a pen. All right, so I just cut my degree measure in half. So let's cut my radian measure in half. So I now know that pi corresponds to 180. I can go even further. Half of a half is a quarter. I could go that route. So I could say a quarter of 2 pi to get me this location. Or I could work off of this. And I say, how do I get from 180 to 90? I chop it in half. So I'll chop the radian measure in half, pi over 2. All right. We could go in order if we wanted to, but generally want to grab the obvious stuff first, I think. Or what could be considered obvious. So then, down the y-axis, we have 270 degrees, because each quarter turn is 90 degrees. 90, 180, next would be 270. All right, so 270 is 3 90-degree turns. 90 degrees is pi over 2, so 3
pi over 2
of those pi over 2s. So 3 pi over 2. All right, so I don't need a formula for that, and you shouldn't either. That's the point. I oftentimes, because eventually, this wasn't a quiz, but eventually you'll be taking quizzes, like 10 of them, roughly, for the end of the year. The first one, you'll be like, oh, dang, I don't want to do this. Maybe you don't do so well on it. But then the 9 that follow, they're like guaranteed 10 out of 10s. So then you start looking forward to them.
Are they all just like this?
Exactly like that. Yeah. So, it's a test where you know what the questions are in advance. And it's not, and it doesn't have any calculus on it. But it should be something that you look forward to, not dread. So. Except, for the folks who are like, oh yeah, that unit sorter, he's going to do that. Yeah, that's going to happen soon. Really got to get on that. I'll look into it tomorrow. Then you walk into class, and there I am handing them out, and you're like, crap. I don't know how to do it yet. That was on tomorrow's agenda. All right, I guess I'm going to take the big goose egg on this one. Yeah, hopefully that doesn't happen, but me giving this little spiel right now should hopefully stave that off. Anyway, the special angles, 30, 45, and 60 degrees. You go through geometry, algebra 2, and pre-calc, and at the end of those courses, it might feel like these are the only angles that exist, because that's how much you investigate these particular angles, excluding pretty much everything else. And there's a reason for that, because these are the clean ones. 15 degrees, 75 degrees, those are good too, but they're not as clean. Radical 2 over 2 is clean. Radical 2 minus radical 6 over 4, that's not clean, right? It's not as ugly as some disgusting decimal, but it's not a nice looking fraction, right? These are going to give us the nicest, right? So the radian measures associated with these. Again, I don't need a formula for that. I just need to know a fact. That fact is that 2 pi and 360 degrees are the same, which led me to the one that I like even better, this one. Pi and 180 degrees are the same. Because then I can say, and I think I heard somebody saying this, what do I divide 180 by to get 30? And that's a good question, because that's going to help me figure out the radian measure at 30 degrees. Divide by 6. So take the pi and divide it by 6. What do I divide 180 by in order to get 45? 4.
Can you do this with 90 too?
You could do it with 90 also. To an extent, but then you get to the 60 and you got to move on to something else. All right, 180 divided by what gives you 60? 3. All right. But you might even look at it and say, well, once I got the 30 degrees, I can get 60 just by doubling the radian measure. So 2 pi over 6 becomes pi over 6. So you can get a bunch of different ways. But the moral of the story is going to be, we don't even want to do it that way. We want an even shorter approach. Because when I give you these quizzes, they're not going to be full period quizzes. They're going to be like exit tickets. You'll have like 5-7 minutes at the end of the class to do it. So you don't want to be taking a heck of a long time to work these things out. So we want to streamline this approach, right? So in terms of the angles, I know that there's going to be a 30, 45, and 60 degree reference angle in every quadrant. So I can do it one of two ways. I could subtract 30, 45, and 60 degrees to get these. Or I could recognize that there's a pattern there. Starting at 0 to get to 30, I'm increasing by 30. That's easy enough. Then 15, 15 again, and then 30. That pattern is going to repeat itself in every quadrant. Increase by 30, then 15, then 15, then 30, all the way around. So 90 plus 30 will give you 120. Add 15, you get 135. Add 15, you get 150. Add 30, you get 180. Again, 30, 15, 15, 30. So 210, 225, 240. Add 30, you get 270. 30, 15, 15, 30. So 300, 315, 330. And then finally 360. So I have all my angles in degree form. But again, they're a means to an end, because I don't need degrees, I need radians. I'm only reporting really the degree counterparts just so I can figure out what the appropriate radian measures would be in each quadrant. All right, so I'll look at, for example, the 120, that's double 60, so I'll double the radian measure. So at 60, I have pi over 3. If I want to double that, it's going to become 2 pi over 3. One 135. That's 1, 2, 3 45 degree movements. So 3 pi over 4. And that's the other thing to keep in mind, is that these aren't static values. They're actual angles that are the results of movement. So when you have 135 degrees, it's because there was a line that swept through an area that corresponds to 135 degrees. So that's the visual part of it that you only really get with the unit circle. You don't get that from a hard chart. All right, 150, I'm really bashing the hard chart. 150, yeah, 5 of those pi over 6s will get you there. But again, taking too long. So it's nice to know this stuff, to see where it's all coming from. It's really just multiplication, but I want an even shorter approach. What I notice here is that all my denominators are 6, 4, 3. It's going out from the x-axis. So that's something that you can rely on. That's going to be the case throughout the entire circle. So I can just go through and make all my denominators 6, 4, 3 as I work outward from the x-axis. So 6, 4, 3 double play. 6. May sound dumb, but that's actually how I remembered it. 6, 4, 3 double play. The numerators in my second quadrant are always 1 less than the denominator. So you notice that relationship. 6, 4, 3, the numerator coefficient is always 1 less. In the third quadrant, I mean, we could do the multiplication to justify it, but I think you'll believe me. The numerator is going to be 1 more than the denominator. So we're going to get 7 pi over 6, 5 pi over 4, and 4 pi over 3. Again, you can do the calculation if you want. And in fact, maybe you do it this way and you double check with the calculation. 240 is double 120. So double 2 pi over 3. You get 4 pi over 3. Right? So you could do it that way. It's not that much of a waste of time. But this is definitely quicker. But it requires you to know the facts. Right? In the fourth quadrant, my numerator is twice the denominator minus 1. So double your denominator. This has been happening all day. Well, double the denominator and subtract 1 from it. I'll fix this in a sec. So we have radical 3 over 2 and 1/2 to start. All right, the denominators are always 2. That's something you can rely on. There's a nice 30, 60, 90, 45, 45, 90 explanation for this with Pythagorean theorem, but it's kind of not overly necessary. So radical 3 over 2, radical 2 over 2, and then 1 over 2. So it's in decreasing order. The other coordinates go in the opposite direction. So 1, radical 2 over 2, radical 3 over 2. All right. These two are, I think, naturally reverses of one another, because if I were to create triangles corresponding to each of these angles, they'd both be 30, 60, 90 right triangles. Just the 30 and 60 degrees would be in opposite locations. So it makes sense that these values would be in opposite locations. This one, in an isosceles right triangle, 2 sides are congruent. So if I were to make a triangle out of this, the 2 legs would be equal to one another. So that's why these 2 are exactly the same. But once I have these, it really is just a matter of knowing the appropriate negations. All right. So if I'm reflecting a coordinate over the y-axis, which value am I negating, x or y? I'm flipping over the y-axis, x. So take all the coordinates that I just wrote, rewrite them, but give all the x values a negative sign. All right, if I flip something over, if I flip a coordinate over the x-axis, what am I negating? Just the y. All right. In the third quadrant, they're both going to be negative. All right, but basically all I'm going to do here is take every coordinate that's in the northern hemisphere and negate the y value, put it in the southern, and we're good to go. So negative radical 3 over 2, negative 1/2. Negative root 2 over 2, comma negative root 2 over 2. Negative 1/2, negative root 3 over 2. All right, and so there's your completed unit circle. And it's like, oh, I mean, you don't see the counter on here, but this video is about 20 minutes long. And you're like, it just took us 20 minutes to do it. How are we supposed to do it in 5 minutes? Well, you're not going to be explaining your thought process every step of the way. That's one important piece. And also, some folks will end up doing this because they don't believe me until the moment of truth. But they're going to be taking the 30 and multiplying it by pi over 180 and simplifying, then doing it for 45, then 60, and then the bell will have rung. And I'll be like, so you plan on turning in this quiz at some point? And they're like, well, can I have a few more minutes? I was like, well, how much do you have done? Well, I'm on the first quadrant. We're like, all right, so you're 20 minutes in, and you're only a quarter of the way through. I gotta go. Like, yeah, so what that means is that you're going about it the wrong way. So the streamlined approach is to know the progression. Denominators are all the same. 3, 2, 1, radical. Opposite direction. Increase by 30, 15, 15, 30. 6, 4, 3, double play. Pi in the first quadrant. Denominator minus 1 in the second, denominator plus 1 in the third, twice the denominator minus 1 in the fourth. Okay? When it all comes down, you know, to the end, I guess, you're ready to turn in your unit circle, provided you actually did it right side up, because that seems to be a thing that happens. Like, people do the entire unit circle, but then realize they've done it upside down. I don't know how it happens, but it'll happen to somebody. The only thing that you're probably gonna, if you're gonna forget something, the only thing you're gonna forget is gonna be these bad boys right here. I don't know why, but people all the time forget the 180 and the 360. I don't know. Sometimes just flat out leave these two things, the 360 and the 2.5, they just leave it blank. Like, I don't want to take off credit when that happens, but you didn't fill in the whole circle. That was the only direction. It says fill in the circle. Like, there's like blanks and stuff. Like, if there's a blank that doesn't have stuff in it, then you haven't fulfilled the requirements. Like the parts where it says positive and negative, we're not going to worry about that. But everything else, you need to have something written there, right? I mean, there's some things where it's like common sense. How could you fill in everything else if you didn't know that 360 and 2 pi were the same? Like, it seems nitpicky that I'm taking off for that, but I'm going to take off like a half a point, right? So don't put me in a position where I have to do that, right? Now, understand, folks, I spent an entire period going over the unit circle. An Algebra 2 concept in a calculus class. How important do you think this is to what we're learning? Very, very incredibly important, right? So take some time.